All right, hello everyone, and thank you for waiting. So we'll get started now. If you haven't yet, feel free to log into juliabox.com. That's where we're hosting remotely a bunch of Jupyter notebooks that I'll be using today. And so I'll show you after a couple of slides how to get set up with JuliaBox for those of you that are unfamiliar. And then you can dive right into playing around with Julia code without actually doing any prior installations. So first off, I'll introduce myself. So my name is Jane Harriman. I work for Julia Computing as their Director of Diversity and Outreach, and one of the goals of the work that I do is to make Julia more accessible by way of offering tutorials and other teaching events to help you get more familiar with Julia if you're a new user or a prospective new user. The tutorials that we have upcoming online get posted on julialang.org on the Learning page. So if you were to go there, you would see the screen that I'm showing now, where you'll see both a prior version of this tutorial, where this tutorial, the Intro to Julia tutorial, runs once a month, and also when we have other tutorials scheduled to take place on broader topics or other topics within the Julia ecosystem. Those will also get posted on this Learning page. In one of the notebooks that we'll cover today on JuliaBox, specifically notebook 12, at the very end of the tutorial, there is a link for, I'm hearing that my noise is low, so I will just try to speak up. And if that continues to be a problem, let me know and I'll see what I can do. So yes, at the end of notebook 12, there is a link requesting feedback on the content that I cover today. So if you can take a minute or two just to answer those 4 questions, it's really helpful to us to see how we're doing and how we can better target the people who are showing up for these events. And so with that, I'll do a little bit of motivation for why we might be interested to learn Julia before we dive right into the tutorial itself. So I'll talk about why we want another language, why the Julia language is getting developed in the first place. And then I'll talk about an application of Julia and show what it looks like to use Julia in practice before diving into the tutorial. So first off, why do we want another language? I like to show this sort of periodic table of programming languages created by a gentleman named Paul Bowler that I found online. And you can see here that different programming languages are color-coded by their characteristics or what they bring to the table. And so the natural question is, with all of these and more programming languages out there, why is a new programming language like Julia being developed? What niche does it fit into, and what needs does it serve? And the idea is that even with all the many programming languages out there, we still have something called the two-language problem. And so I'll define that for you so that you understand what the two-language problem is, because this is a problem that Julia has been addressed to solve. So the two-language problem arises from this traditional observation that languages are either performant or productive. So on the one hand, we have these classically lower-level languages like Fortran and C that allow us to write code that ultimately generates really efficient machine code and executes very quickly on our machines. But it takes us longer to get up and running and longer to get up and writing code in some of these lower-level languages. Whereas on the other hand, we have these traditionally higher-level languages that enable us as programmers to be more productive. So these are languages like Python, R, MATLAB. Here I have Ruby listed. Let me see, what another one? Some might say, maybe Java. And the idea is that, then we are forced to, face this trade-off traditionally between these, languages that allow us to write really efficient code and languages that that allow us to write code efficiently. So this trade-off between performance and productivity isn't truly, just a dichotomy here. Really, the third variable that we're implicitly considering there is generality, because there are special libraries or domain-specific languages that will allow you to write fast code very easily. So, for example, if you're familiar with the Python ecosystem, if you are working exclusively with arrays, you might find yourself working a lot in NumPy, because NumPy allows you to work really quickly and easily with arrays, and you're also generating really efficient machine code at the end of the day because things have been super optimized in C. under the hood in NumPy to handle arrays well. But then, in that case, you're only able to work with certain types of data structures, and thereby the scope of the work that you can do with NumPy is less general. It's necessarily limited. And so what we're really facing here is a trichotomy between generality, performance, and productivity. And this trichotomy classically forces people to not be able to choose one tool that meets all of their needs. Therefore, they have to use multiple tools to meet all of their needs. And they'll end up working in two different languages, typically one for prototyping and one for production. So what that will look like in practice is that a programmer or a developer might start by working in a language like Python or MATLAB again, because those languages will allow them to get up and running quickly and writing code easily. And then once they have something working, once they sort of have like a proof of concept, they'll then translate that code to a lower level language once they get to a point where they really need their calculations to hit scale and to execute quickly, when the machine time becomes much more valuable. So they end up working in two different languages, and that's where this term, the two-language problem, comes from. And this was the issue that Julia was designed to address, with the idea being that you can have a language that looks like Python, feels like Lisp, and runs like C. So a language that offers productivity, generality, and performance all at once. So when I claim that Julia offers all of these things, brings all these different things to the table, I'll now talk through what I mean when I say that Julia offers each of these characteristics. And so we'll start by talking about performance. Now, in one of the tutorial notebooks that I'll do later, I think it's now notebook 9, called Julia is Fast, we're going to do some performance benchmarking. And so what we'll do in the context of that notebook is that we'll benchmark different implementations of a sum function. And so we'll look at both built-in versions of the sum function and handwritten versions of the sum function. This sum function in particular is going to take some vector, and it's going to add together all of the elements of that vector. So for the purposes of benchmarking, we're going to be passing in a vector that has 10 million elements, and then seeing how long it takes to add together those 10 million elements with each of the different implementations of sum. And aside from the built-in versions of sum that we'll be looking at in Python, NumPy, and Julia, we're going to be looking at handwritten versions of this sum function in C, Python, and Julia. And so when we time how long it takes to add together these 10 million elements of a vector in each of these languages, what we see is that it takes about order of 10 milliseconds in C to do this operation. Then when we go from C to Python, it's going to take order of 500 milliseconds. And at the end of the day, when we go from Python to Julia, we're going to be back down to order of 10 milliseconds. So Python is going to be taking more than an order of magnitude longer than C to run, but Julia is going to be really pushing to get down to C speeds. So beyond performance, I said that Julia offers productivity, or ease of use for you as a coder. And one way that we can talk about productivity is by looking at the syntax of Julia and seeing how it compares to the syntax of other high-level languages. So on this slide, what I'm showing are code samples that we actually use to implement handwritten versions of the sum function in Python and in Julia side by side. And so what we're seeing here is that using the same algorithm to express sum in each of these languages, we end up with really, really similar code with really just differences in a few required keywords. So the differences that we're seeing here are all highlighted or bolded. And so we're seeing that there are a couple differences in required keywords. Like in Python, we use the def keyword to define a function. In Julia, we're going to be using the function keyword to define a function, as well as the end keyword to terminate for statements and function declarations. Then in Python, we have these required colons, which we don't need in Julia because we have these end statements. But other than these couple minor differences in the syntax, we can see that we can express ourselves in Julia in really similar ways as we can in Python, this other language that's known to be high level and relatively easy to use. And it was this sort of minor difference that really got me excited about using Julia. So I didn't mention this at the beginning, but I'm also a Python programmer. I started off teaching myself to program in Python a few years back, and I was using Python primarily for my research in graduate school. And at some point, I had a friend who was really excited about Julia, who took a piece of code that I had written in Python and then translated that code to Julia. And I was able to see right away that, first off, the code that he had written looked pretty similar to the code that I had written. I mean, again, there were just like a few minor syntactic changes. But at the end of the day, when we benchmarked the two functions, the one that I had written in Python and the one that he had written in Julia, there was more than an order of magnitude improvement in going from Python to Julia. And so I started to see that maybe I could get the benefits of speed without needing to pay such a toll to learn a new language, because learning Julia, particularly when coming from another high-level language, is relatively straightforward. So the third thing that I said Julia brings to the table is generality. And this is what we were getting at when in that tagline that I showed earlier, where we say that Julia feels like working in a Lisp. So what we mean by this is that Julia offers metaprogramming facilities. You can do macro programming in Julia. The design paradigm of Julia is multiple dispatch. And overall, Julia is a very general, powerful, and expressive language. And it's these features that allow Julia to be mostly written in Julia itself. And one of the things that's really cool about the fact that Julia is mostly written in Julia, as you delve deeper into the source code, is that this really starts to blur the line between users and developers of the language. So once you know the language well enough to be using it for your own purposes in your work, you'll find that there's not a huge barrier to actually looking inside the source code and having a sense of what's actually going on under the hood to implement the functions that you are using. And so it's sort of a common story within the Julia community that someone who has come to the language just to use Julia as a tool will end up tweaking the source code and becoming a prolific contributor because they find that they have fun actually making their own modifications to some of the source code in the base language. All right. So that's my, why do we want another language intro. And now I'll quickly walk us through an application of Julia so we can see what using Julia looks like in practice. In particular, I always like to talk about the Celeste research project because this is a really great case study of using Julia out there in the real world. And so what the Celeste research project did was that they took data from the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey was an effort to collect data on 35% of the visible sky, and it brought in about 178 terabytes of data. So that's, for your reference, 1.78 times 10 to the 14 bytes. And here I've provided some comparisons to give you a sense of scale for how much data that actually is. So what I'm showing here is that if you wanted to store 178 terabytes on DVDs, you'd need, order of 25,000 or more DVDs to do so. And then my silly comparison is that if you wanted to print all of this data on written paper and then lug that paper around, you would need more than 150,000 pickup trucks to lug around the amount of data required the amount of paper required to store that data. And so we had a huge data set, or there was a huge data set, and the first decade or so that it was around, there wasn't a whole lot done with it because it was, or at least my understanding is that it was a relatively overwhelming data set. But then the Celeste research team came together and they decided to write software exclusively in Julia that would run on supercomputers up at NERSC, so at Lawrence Berkeley National Lab in the Bay Area. And using Julia as their software, along with these supercomputing machines as their hardware, the Celeste research team was able to catalog 188 million stars and galaxies from this giant data set. And so this meant taking in all of that data and identifying the morphologies, the colors, the brightnesses, the locations of 188 million astronomical objects. Now, beyond the fact that they were able to do this massive calculation is the fact that they were able to do this massive calculation in under 15 minutes. During which the machines that they were using were running more than 1.5 petaflops per second, and this figure was what enabled Julia to join the petaflop club, or to be the third language and really the first high-level language to be able to hit over 1 petaflop per second. Now, in doing this calculation, Julia made use of over 1 million threads, over 9,000 nodes, which I think came out to something like 650,000 processors. So yeah, it looks like there are probably about 2 threads per processor. And so these numbers are meant to show that Julia can distribute well on next generation machines as we move more towards parallel computing. All right, so the Celeste project itself is pretty impressive, but the big deal here is like, what did Julia bring to the table, and why is this a good case study for Julia itself? And the answer to that, or maybe the first answer that you would come up with, is like, well, Julia is meant to address the two-language problem, and so therefore what Julia brought to the table was greater efficiency. Maybe the project got done a little earlier than it would have otherwise if multiple languages had been needed to complete the project, because maybe the developers were able to skip a step because they didn't have to translate, for example, their MATLAB code into their C code. So yeah, maybe they finished the project a little earlier than they would have if they had used Julia, or if they hadn't used Julia. And that's true. There was definitely greater efficiency introduced into the process of developing the software for the Celeste project. But really the impact of using Julia on this project was more profound than that. And the reason is that the two-language problem that I described earlier looks, it gets worse the more people that you bring to the table. So a single person might face the two-language problem and find that they're rewriting their own code after their first implementation. But when you have a larger software project, when you have a team of developers working together, the dynamics of the two-language problem get worse. And so what the Celeste research team actually I guess looked like was that the Celeste research team was composed of people with backgrounds in statistics. They had domain scientists on the team, they had computer scientists on the team, and what this meant in practice is that when you have a team with all of these different backgrounds coming together to write one piece of software, when a team like that faces the two-language problem, the team is probably going to break up into two different camps, where your domain scientists are going to start with your first implementation, or that first prototype of the software that you need in a high-level language. And it's really only when they're done that they're probably going to pass the baton off to the computer scientists, who are going to then do the translation from a high-level language to a lower-level language that really hits peak speeds. And so the fact that rather than needing to face this two-language problem, the Celeste research team was able to work in Julia meant that the entire research team, the domain scientists, the computer scientists, the statisticians, everybody was able to work in the same code base and the same language from the beginning. And so that meant that the team was really much better able to function as a team and to work together. So this meant that they could iterate more rapidly, and thereby the science and the implementation of the science were able to grow together, as the domain scientists were trying out new things to figure out what they needed to do to classify all the astronomical objects stored in the data, while optimizations were happening in parallel on the same code base. And so beyond the Celeste research team, which was composed both industry and academic partners, we're starting to see Julia uptake across industry as well. So on this slide I have some industrial partners that are either hiring Julia programmers, or have Julia programmers at their institutions, or and that sort of thing. So for example, BlackRock in finance, Microsoft, Amazon, Aviva is another really good case study to read. If you go to the Julia Computing case studies page, you can read about what some of these companies are actually using Julia for in their work. And I'm trying to think if there are any big companies I'm aware of that aren't shown on this slide, and I'm blanking out right now. But yes. So this should give you a sense of where Julia is being used in industry. Beyond that, we had the 1.0 release earlier this month. And as of this month, we're at a total of over 2 million downloads. I didn't check these numbers right before starting the tutorial, so these numbers are from a couple weeks ago. Maybe they've gone up since then, I'm not quite sure. But we have a package ecosystem that has over 1,900 registered packages at this point, and we're seeing a bunch of growth. we're expecting that to increase even more now that we have actually hit language stability. And so we're excited that you're here to do this tutorial, and hopefully beyond this tutorial you'll be interested in joining our growing community of users. If you need help beyond today with learning the language, there are lots of resources out there to help you, beyond this intro tutorial. So there are active communities on Slack, Discourse, and GitHub. GitHub is where all of the language development is happening. And then we have active, both developers and user communities on Slack and Discourse. So if you have any question about use of the language, those are usually the best places to go. If you are looking for something particular that you're not able to find in any of these three places, I have my email address shown on this slide so that you can reach out to me, and hopefully I can connect you with somebody who can better answer your questions if you find yourself stuck. So with that, we can dive into the tutorial. And again, if you haven't gone there yet, you can log into juliabox.com, where you'll have some Jupyter notebooks that you can use. So let me switch over to JuliaBox. Let's see. Okay. Let me see if I can get to the home page just by doing this. No, I'm gonna log out just so you can see my background as I log in case anybody hasn't done this yet. So when you go to juliabox.com, you'll have the option to log in with GitHub, Google, or LinkedIn. So I think, I usually log in with GitHub. Once you log in with GitHub, what you'll see is a series of directories, one of which is going to be labeled tutorials. And so today we'll be inside the tutorials directory, furthermore inside the Intro to Julia subdirectory of that. So in a second I'll show you what I mean. Okay. And sometimes, so JuliaBox is bringing on additional nodes as people log in, and so sometimes, when there's a bit of load, there's a bit of a delay as more nodes are being brought online for our purposes. Let's see. Curious to see how many people are watching the tutorial given the delay. Oh wow, we have 81 people. That's fantastic. Okay, so yeah, that's why JuliaBox is a little slow right now. Give it another minute. Okay, great. All right, so I'm on JuliaBox. This is the tutorials directory that I promised we would see. So we can click on tutorials. Once we're in there, there are a few different folders that you could go into with different topics and also different associated videos if you go around on our YouTube channel for Julia Lang. Also, one distinction, so this confusion has been coming up a bit. Julia Computing is distinct from the Julia Language Project, and I make it confusing. It's already a confusing distinction, but I think I make it further confusing by just using the pronoun we and not referring to who exactly I mean. So if you go to the Julia Language YouTube channel, there are playlists for tutorials, and you can find videos associated with these different directories. Like we have a tutorial on data frames, a version of this Intro to Julia tutorial in Spanish. There's an Intro to Julia for Data Science tutorial done by Huda Nassar. Today we're in the Intro to Julia subdirectory, and the notebooks that we'll be going through today are notebooks 0 through 12. And so if we go to this first notebook, on Jupyter Notebooks, the purpose of this notebook is to get you familiar with the environment that we'll be using today on JuliaBox. Another note that I'll make about the structure of this tutorial is that the first notebooks 1 through 6 are really meant to give you a sense of the syntax in Julia, and then we'll start talking more about the package ecosystem and how to plot in notebook 7 and 8, and then we'll talk a little bit more about benchmarking in the language, the design paradigm, and linear algebra in the later notebooks. Another note is that JuliaBox is not yet on version 1.0. You'll see here in the right-hand corner of my 00 Jupyter Notebooks notebook that I'm on Julia 0.6.2. During the tutorial today, I'll be pointing out some of the things that have changed as we go from 0.6 to 1.0. And JuliaBox will very shortly be on 1.0. So the next tutorial we do will be on the 1.0 version of Julia. But for now, we can get started in this version. So first off, if you haven't worked in a Jupyter Notebook before, you'll see that there are these different cells in the notebook. So we have these cells that contain Markdown, and then these other cells that contain code. The Markdown cells are there to provide explanations and text, and then we can actually execute any of these cells that are meant to have code in them. The code cells are a little bit darker gray and then have these input denotations next to them on the left. So to execute a cell, what you would do is you would select that cell with your cursor, for example, and then you can hit Shift and Enter, Shift and Return, or you can hit this Run button here. Alternatively, you can go to Cell in the menu bar, and you could go to Run All, for example, to run an entire notebook. So by default, in a Jupyter Notebook, when I run a cell, I am going to see printed to the output whatever is in the last line of that cell. So here we're printing the number 4, but we're not printing the number 2 from this first edition. If you want to suppress the output so that you don't see anything being printed to standard out, you can put a semicolon just after the last line of a cell. Now, if you want to get documentation for any Julia function you haven't seen in this environment, you can put a question mark before that function name. So here we're saying question mark println, and that's giving us documentation for the print line or the println function, which is basically the most common way to print in Julia. Also, I should say this help mode that we're getting here with the question mark, that works in the REPL just as well as a Jupyter Notebook. So that's a standard Julia feature and doesn't have to do with this Jupyter Notebook environment. Similarly, if you're in a REPL environment or if you're in a Jupyter Notebook, you can use shell commands from within your Julia environment by preceding your shell commands with a semicolon. So here if I say semicolon ls, I'll see all the notebooks in my current working directory, and I can see the name of my current working directory if I say semicolon pwd. So that's it for this environment. And now if we go to notebook 1, that'll show us some basic Julia commands. So in particular in this notebook, what we're going to see is how to print in Julia with that println function, how to assign variables, how to comment, and then some syntax for basic math. So first off, to print in Julia to standard out, you can use this println function and then just enclose whatever you want to print to standard out inside that function call. So here we're printing the statement, I'm excited to learn Julia, as a string. If you want to assign variables in Julia, you don't have to specify the types of those variables. So for example, here I am creating a variable called myAnswer, assigning it to the number 42, and then I'm using this type of function to see that my answer is recognized as an int64. Similarly, Julia recognizes that this variable called mypi is a float 64, and then here I've assigned a string to the smiley cat emoji. So generally, or rather, programming with emojis in Julia is a good example of Julia being generic. And one of the things that means, I guess, one other note I'm going to make before I go into my little emoji spiel is that once you've assigned a value of any type to a variable, there's no issue with reassigning that variable to a different value of a different type. So, even though smiley cat emoji is assigned to a string here, we can reassign smiley cat emoji to an integer. We see now that smiley cat emoji is an int64, and there's no issue there. Okay, so now for talking about generic code with emojis, given that we can code with emojis and create variables or assign values to variables that are emojis, I here can assign the smiley face to the number 0 and the frowny face to the number -1, and that allows me to evaluate Boolean statements like this one where we see that smiley cat emoji plus frowny face equals a happy face. And that's now a true statement in my code. Now, if you want to comment in Julia, you can use a single line, or you can create a single line comment using a single hashtag or a single pound sign. So nothing in this code block or in this line is now going to get executed. And if you want a multi-line comment, you can close your multi-line comment in between pound signs and, rather a pair of pound signs and a pair of equal signs. So again, nothing inside this is going to get executed now. And then the syntax for basic math should look pretty familiar. We have addition, subtraction, multiplication, division, exponentiation. If you're coming from a Python background, will look a little different in that we're using the caret sign rather than the double star. That's the one that still trips me up if I ever have switched back to Python for any reason. And then we have the modulo operator here to give us remainders and that sort of thing. At the end of most of these notebooks, I have some exercises for you to try out. And so, if you're a little ahead of the game and you have time while I'm talking, feel free to try out these exercises. And if you get stuck in anything, ask in the live chat that we have going in parallel with this video. And if you don't have time now, then maybe after the tutorial, play around with these and see if you can't get a little bit more comfortable working in this environment. Okay, so that's it for Notebook 1. And I will now go to Notebook 2, which is on strings. So in this notebook on strings, we're going to see how to create a string in Julia and then how to interpolate and concatenate them. So we see first two ways to create a string. The first I'm using when I create this string called S1, and the second I'm using to create the string called S2. So in this first type of string, what we're seeing is that I have text enclosed within a single pair of double quotation marks. And in the second way of creating a string, I have text enclosed within 3 sets of double quotation marks. One of the things that's different about these two different types of strings is that in the second type of string, I can add formatting to my string. So for example, here I added a few return characters, and then Julia can recognize that I intentionally added these new line characters into that string. An additional difference is that if I want to, for example, use double quotation marks inside the first type of string, I can't do that because it adds ambiguity as to where the string actually ends. Like, is the highlighted part now, the string I'm supposed to be interpreting, or is it, this entire thing? And that's confusing. So we get an error here. On the other hand, if we want to put the word errors in quotations here, we can do that in the second type of string where we're using those 3 sets of double quotation marks. Because it's unambiguous where our string ends. The third thing to note here is how to not create a string in Julia. So unlike in Python, for example, you cannot create a string with a pair of single quotation marks in Julia. So when we ask for the type of the letter A inside single quotation marks, we're seeing that this is a char rather than a string. So this is a character. And therefore, we can enclose only single letters or single characters inside a set of single quotation marks. So if we try to enclose more text inside single quotation marks, we're going to get an error here. Now for string interpolation. Okay, just checking Slack. I haven't received any more complaints about things that are unclear or not being able to hear me, so hopefully we're good to go. Okay. So, string interpolation, yes. So if you're not familiar, the idea of string interpolation is that we are going to throw the value associated with some variable into a string. So that means that, if I create, for example, here are these 3 variables, name, num fingers, and num toes, maybe instead of using the word name within a string, I actually want to throw in the value associated with the variable name, which is now the string Jane, into a string. And if I want to do that, I denote that I actually want the value tied to an existing variable with a $sign, as I've done here. And so when we execute this code, we see that now we've thrown the value of the name variable and the value of the num fingers and the num toes variables inside the strings that we're printing to standard out here. Additionally, beyond just inserting an existing variable inside a string, you can actually evaluate an expression within a string. So here what I'm doing is I'm enclosing the expression that I want to evaluate inside parentheses, and then I have a single $sign to the left of the starting parenthesis. So here we're actually adding 10 and 10 together, we get the number 20, and then we throw the number 20 inside the string. Now, to concatenate strings, what we mean by concatenation is that we want to take multiple strings and add them together to get a single longer string. So I'll show a couple different ways to do string concatenation here. First off, we'll create the strings S3 and S4, and then we're bringing back smiley cat emoji as now the number 10. If we call the string function on the strings S3 and S4, we get a single output string. So the string function does string concatenation for us. Also, the string function can take arbitrary numbers of input arguments and arbitrary types of input arguments. So if I call the string function on now 3 input arguments, I'm getting the response to my first concatenated string, how many cats is too many cats, where the response is now I don't know, but 10 is too few. And here we had 2 input arguments to string, here we had 3 input arguments to string. That's all okay. It's also okay that here one of our input arguments to string is the smiley cat emoji. There we're just interpolating that value into our string. Now we can also use the star operator for string concatenation. And so when it looks like we're multiplying together the strings S3 and S4 and getting the output string, how many cats is too many cats. One exercise I do want to draw your attention to, just because this is sort of fun, is that, so the star operator is what gets called under the hood whenever you use this exponentiation operator. So if I say high to the 1000th power, what I'm really doing is I'll put a comment here. It's really like I have this high string and I'm multiplying high by itself 1,000 different times. And so if I run this, I get one very long and friendly string. Okay, so that's it for our notebook on strings. And with that, I will now go to notebook 3, which is on data structures. Okay, so in this notebook, we're going to talk about tuples, dictionaries, and arrays. So we'll talk about how to create them and then a little bit about how to work with some of these data structures. For those of you that aren't familiar, just some high-level differences between tuples, dictionaries, and arrays are that tuples are stack allocated. What that means in practice is that they are immutable. So once we've created a tuple, we can't mutate them, we can't change them or alter them in any way. We're stuck with the tuple that we first created. Tuples are ways to store ordered collections of elements. Another way to store ordered collections of elements is to create an array. Arrays, unlike tuples, are mutable, so we can create them and subsequently we can edit them. We can add items, remove items, change existing items. And then aside from tuples and arrays, we have these things called dictionaries, where dictionaries, they're mutable, so in that sense they're like arrays. We can change them after we've created them, but they do not contain ordered collections of elements. Instead, they are hash tables, and we'll see in a second that means we can create sort of associative pairs of data inside a dictionary. So the example of a dictionary that we'll build later will be this one called My Phone Book, where my phone book, like what you might think of as an in-person, a live phone book, is that you have names associated with numbers, and we're going to refer to those entries as key value pairs. But we'll see all that in a second. So if that was too much information at once, don't worry about it. We'll get to it. So first off, tuples. So if you want to create one of these, ordered collections of elements that you can't update, you would store the elements that you want to store inside a pair of parentheses. And so my first example of creating a tuple here is this one called My Favorite Animals, which contains the strings penguins, cats, and sugar gliders. If you want to look inside the tuple that you've created, you can index into it, and you do that by throwing a pair of square brackets after the name of the tuple, and then you throw the number of the element that you want to grab. And so Julia is a one-indexed language. What I mean by that is that in Julia we start counting with the number 1. That will probably enrage some of you and make others feel comfortable. Languages, and just, for context, languages like C, for example, and Python start counting from the number 0. So that can be a little confusing if you're coming from a different, a language that indexes things differently. But yeah, here we see that when I ask for the first element of my favorite animals, we're grabbing the element penguins, the first element of that tuple. Now, if I wanted to update the first element from penguins to otters, I can't do that because tuples are immutable, so I get an error when I try. For those of you that don't know what a sugar glider is, I think you should be able to download an image of a sugar glider here with this download command. I think I already had it downloaded for me, but oh, we need to use the images package. Right, this code is a little out of order. If this isn't working for you, this use images line should just be before the load. So the images package is going to allow us to load a picture of a sugar glider. While that is running, I'm going to start talking a little bit about, oh, here we go. Okay, this is a sugar glider. It is probably the best marsupial. They're like flying squirrels, a little, but they're more cute, I think. Fun side note. Okay, now that we know what a sugar glider is, we want to know what named tuples are. So in 1.0, but not in the version that we're using today, you can create named tuples. So beyond simply ordering your elements inside, a pair of parentheses, as we've done here to create my favorite animals, you can actually add names to the entries of your tuple such that you could access those entries of your tuple both by indexing, as we've done here, and also by using those names that you've assigned to the entries. So what the syntax for that is going to look like is shown here. So here we could have created, if we were in 1.0, a version of my favorite animals where we have a favorite animal that we know is a bird, one that's a mammal, one that's a marsupial, and then we have, for example, these labels bound to each of these elements, and that means that I could still look up, the first element of my favorite animals to return the string penguins, or alternatively, if I just said my favorite animals dot bird, I could grab penguins that way too. So I wouldn't have to remember the order of my collection of elements in order to index into, or rather to grab pieces of data that I know are in there. Okay, so now we've talked about tuples, named tuples, and of course sugar gliders. We can talk about dictionaries. So one way to create a dictionary in Julia is to use this dict constructing keyword. And so what we would do in a call to dict, we can create an empty dictionary. We could do that simply by saying, dict with, open parentheses and then, nothing inside the parentheses. Or we can initialize a dictionary to have data in it already, in which case we would feed it, at the time that we're constructing the dictionary, key value pairs. And the syntax for doing that is to, inside these parentheses after dict, put each key that we want to the left of an arrow that we create from just an equal sign and a right pointing arrowhead. And then we put the value that we want to associate with that key to the right of that. So in practice, what this might look like, I show here when we create this dictionary called My Phone Book. And so here we would say that Jenny, or the string Jenny, is a key. And we would say that this number here is a value associated with the key Jenny. Similarly, Ghostbusters is a key, and this number is a value, or rather this string containing a number, is a value associated with the key that is the string Ghostbusters. Now once you've created a dictionary like this, you can perform a lookup in that dictionary by putting the key that you want to know the value of. So if I want to know somebody's phone number, I would put their name in this instance inside square brackets after the name of the dictionary. So here we're saying My Phone Book, and then we have the key Jenny, or the string that contains the text Jenny, inside square brackets, and then we get Jenny's number. If we want to add another entry to a dictionary, what we can do is that we can use this similar sort of lookup syntax where I'm putting now the new key that I want to add to my dictionary inside square brackets after the name of the dictionary that I'm updating. And then I put an equal sign to the right of that. And to the right of the equal sign, I put the new value that I want to associate with my new key. So here I'm adding the key value pair Kramer and this string that says 555 Filk. And when we look at My Phone Book, we're going to see that we're up to 3 entries now. So Kramer has successfully been added to the dictionary. Another way that you might want to update a dictionary is to remove an existing key value pair, and you can do that using the pop bang command. When I say pop bang, what I mean is that this pop function has an exclamation point on the end of its name, and we'll talk in a later notebook about why some functions end with exclamation points and why others don't. But for now, just know that pop bang allows us to update a dictionary. We're giving the dictionary name as the first input to pop bang, and then we are giving the value from the key value pair that we want to delete as the second input to pop bang. So when we run this, we can then look at my phone book and see that Kramer has successfully been removed. We also note that Kramer's number, in this case the value associated with this key, gets returned when we call pop bang on my phone book. And as I said earlier, phone books or dictionaries are not ordered. So that's to say that if we tried to look for the first element of a dictionary, as I'm doing here, we would get an error because what this is really being interpreted as by Julia is that we're looking for some key called 1, looking for the value associated with that key, which doesn't make sense in this current context because we don't have such a key in my phone book. So we're getting an error. And then the third data structure that we'll talk about in this notebook is the array. So arrays, like tuples, contain ordered collections, but they are ordered collections that we can update after we've created them. And so with that, we can create an array a few different ways, but the first way I'm showing is just by manually typing my elements inside square brackets. And so here we have an array called my friends. One thing I'll point out here is this signature that comes up when we create arrays. Also, other objects. We saw a similar sort of signature above when we created the dictionary called My Phone Book. We can talk about that more in a second. But one of the things that we're seeing here when we get this signature is that this array, My Friends, has 5 elements, so 5 different entries. And then we also see that Julie recognizes this is of the type array. The dimension of the array is given here on the right-hand side of the curly braces that we have following the array word. And so this is a 1D array, and it's in particular a 1D array that contains objects that are strings. So similarly, if we were to look at, for example, the array called Fibonacci that we're creating here, we're again seeing that this is a 1D array. It now happens to have 7 elements, but now Fibonacci contains N64s rather than strings, as in the case of My Friends. There's no issue with creating arrays that contain values of multiple types. So here we're creating an array called Mixture, which is again a 1D array that now contains objects of any type. If we want to index into an array that we've already created, we can do that by throwing the number or the index of the element that we want to grab inside square brackets after the name of the array. So here I'm saying My Friends, then inside square brackets I have the number 3, and so if we were to scroll up, we'd see that we've correctly returned now the third element of that array called My Friends. Okay, if we want to change an existing element of an array, we can do that by using this indexing syntax, and now we would just put an equal sign after that indexing syntax and the name, or rather we would add the element that we want to be the new element at that position after the equal sign. So there we're updating the third element of My Friends. Now if I actually look inside My Friends, we see that Baby Bop has successfully replaced Barney. Okay. A couple other ways that we can edit arrays are to use the push bang and the pop bang functions. So here I'm using push bang. What push bang is going to do is it's going to add the number 21. So it's going to add whatever is in the second input argument to push bang to the array specified as the first input argument. So here we're pushing the number 21 onto the very end of Fibonacci. And so here we see that we've gone from a 7 to an 8 element array. Note that if we wanted to, there's no reason we couldn't add other data structures, with the push command. So for example, I could do something ridiculous, break the Fibonacci sequence, and oops, exclamation, not the number one, push bang. Oh yes, so I can't do this. And now is a great time to tell you why. All right, so as I showed you before, oh, this is great. So perfect. Okay, as I showed you before, Fibonacci, I'm gonna stop adding the number 21, so I'm just commenting this line out since we already ran that. So if we look at Fibonacci, I've already added 21 a few times, we saw that this is an array that contains integers. So what that means is that since Julia has already seen, based on the information we provided when we created the array, Julia has already seen and determined that this array is always going to take integers. So now if I try to push or add to the end of this array something that's not an integer, Julia is going to get angry and return an error. And that's exactly what was happening when I tried to push an array to the end of this, because an array of integers is not the same as an integer. So again, let's see this again, we get an unhappy error. But on the other hand, notice, and you can see this for yourselves if you scroll up, the array called mixture takes any input type. So if I call pushbang and feed mixture as the first input argument, I have no issue with now adding an array to the mixture, adding an array as an element to the mixture array. And now we can see that the last element of mixture is going to be this array that contains the integers 1 and 2. So that's an important thing to note. And we'll talk more about that in the context of dictionaries in a second at the end of this notebook. So let's see. Now if you want to remove elements from an existing array, you can use the popbang command. Notice that popbang in the case of an array only takes one input argument. In dictionaries it took two, because in the case of a dictionary we needed to specify what we were removing from the dictionary. In the case of an array, we don't need to specify what we're removing because we're always taking whatever is on the end. And now, once we run popbang on Fibonacci, we can look inside Fibonacci, see that one of our 21s was removed, but I added 21 a few times, so I'd have to keep running popbang to subsequently remove all the 21s. So after running it a couple times, now we're down to number 13 as the last element of Fibonacci. Okay, great. Let's see, so most of the examples above, until I got to mixture, most of the examples above for arrays were examples of 1D arrays that only contain scalars. So 1D arrays that contain, for example, strings or integers or both strings and integers. But we also can create data structures that contain other data structures, and that's what we did when we added an array as an element to the array called mixture. We could create, from the beginning, an array of arrays, and that's what I'm doing here. So I'm creating this array called favorites that contains arrays. When you look at the signature here, we would read this the same way that we read the other signatures above when we created arrays, where you're reading from sort of the outside in. So you're seeing that this is, favorites is a 1D array, a 1D array, and now the elements inside this 1D array are other 1D arrays that contain strings. Similarly, if we look at the signature that's going to come out of this numbers array of arrays, we see that this is a 1D array that contains 1D arrays of integers. Now, moving beyond arrays of arrays, or for example, you could do tuples of tuples or dictionaries of dictionaries if you wanted to, but you want to be careful not to confuse arrays of arrays with higher dimensional arrays. Since that distinction does exist in Julia. So a 1D array in Julia also walks around by the name vector. I think that's written somewhere in here, but I don't see it immediately. So I could refer to favorites as a vector of vectors. I could refer to numbers as a vector of vectors. Vectors of vectors are distinct from matrices. Now, when I run this rand command, the rand command is creating here a matrix. A matrix is another name for a 2D array in Julia. And what we're seeing is that what the rand command does is that it's generating a higher dimensional array when I pass it multiple input arguments. So when I pass rand the numbers 4 and 3, it's creating a 4 by 3 matrix. Rand will continue to work and generate these higher dimensional arrays as you pass it additional input arguments. So if I say Rand on 4, 3, and 2, in this case, I'm going to be creating a 3-dimensional array, and you can see that with the dimensionality specified there that I've highlighted. And this is a 4 by 3 by 2 array in this case. By default, Rand is always populating the entries of the arrays that it creates with numbers between 0 and 1, but I'll show you later that you can tweak this so that you don't have to create randomly populated arrays of just floats between 0 and 1. A last note about arrays is that when you copy an array, you want to be careful about what you're actually doing. So we've played around a little bit with this Fibonacci array, and then if we wanted to copy Fibonacci, some of you might first be inclined to try to copy Fibonacci by saying sum numbers equals Fibonacci, and you think you're creating this new array called sum numbers when you do this, but you're not. What you're doing in this case, and here, I'll show you first that that's not what's happening. So sum numbers is not a new array. You haven't copied Fibonacci at this point, and you can see that because if you look inside sum numbers, and you look at that first element inside sum numbers, and you change it from what it is here, a 1, to the number 404, you'll see that that update is also going to happen to the array called Fibonacci. So even though we didn't explicitly call Fibonacci and mutate it, it got mutated. And the reason is that when we said sum numbers equals Fibonacci, all we're doing is giving a second name to the array called Fibonacci. We haven't made a distinct one. So if you want to actually create a new object in memory that's distinct from your original array, you're going to need to use the copy function, which is what I'm doing here. To prove to you that the copy function works, I start here by just restoring Fibonacci to its original state. So now we're back to having Fibonacci with the number 1 as the first entry in Fibonacci. And then here I'm copying Fibonacci to get this new array called some more numbers. So now if I walk through the same exercise I did above, and if I say, all right, let's look inside some more numbers, we're going to update that first element to the number 404. Now we can look at Fibonacci and see that Fibonacci is unaltered by our mutation or our update of some more numbers because those are separate objects. And yeah, there are exercises at the end of this that you can play with. I wanna give you the answer to one of these exercises so that you don't get too stuck. The point of these exercises is to show that if you try to add elements or key value pairs to a dictionary where the types of those key value pairs don't match up with the dictionary that you originally started with, you're going to get errors, and then you also want to figure out how to fix that problem. So this is just like the issue we saw above, where when we tried to add an array to the array called Fibonacci, Julia got angry. If we were to try to add the number 911 as a value to the dictionary called My Phone Book, Julia would get angry, and I guess I can show that so that you believe me. Okay, equals 911. Okay, so that's an angry Julia, and the reason that Julia is angry is that My Phone Book only takes strings as keys and strings as values, and that's because when we created My Phone Book, the information we provided suggested that that was what we were going to want. So if you don't want to run into this issue, say you know that you are going to be creating a dictionary that has many different types as keys or as values. What you could do is just create a dictionary that is empty from the beginning, and that empty dictionary then is just automatically going to be here. The dictionary D that I'm creating is going to take any types as both the key and the value. Alternatively, you could explicitly say I want a dictionary that takes any types, and you would do that by adding a type annotation when you create the dictionary. So that's a little bit more advanced. If you don't want to deal with type annotations, you certainly don't have to, but that is one way that you can do it. You could explicitly say I want my dictionary D to accept anything as a key or anything as a value. You could also say I want it to accept anything as a key and only integers as values. So it's with these curly braces that we do that type specification. Okay, so that's it for data structure. So now we're going to go on to Notebook 4. Notebook 4 is going to show us what you're seeing on Julia Box should be different than me. You should see that Notebook 4 is just this loops notebook. Mine is a little, I'm having, yeah, some version control issues here. So yes, you should see that notebook 4 is the loops notebook. So when you go to the loops notebook, what you will see is some syntax for writing while and for loops in Julia. So we'll first talk about the syntax for writing a while loop. Now, a while loop in Julia can be written by using the while keyword right before the condition that we're going to evaluate to see, if it's true and if we should enter the loop body. And then the end keyword denotes the end of the while loop. Typically, we'll put the loop body on the line in between the lines that contain the while and the end keywords. And so my first example then of writing a while loop is here, where we're using a while loop to count from 1 to 10. And then here I have another example of a while loop where we are iterating over this array called my friends and greeting each of the entries of this array. Note that, because we have this end keyword here, it's clear where our loop is actually ending. That means that we don't need to use white space, for example, to denote where the loop ends. And we could add arbitrary amounts of white space here, and the loop would run exactly the same way. So Julia, for the most part, is white space sensitive. When I say for the most part, what I mean is that Julia does recognize that this is a new line character. So if I tried to just remove that new line character, that doesn't work. If I want to denote separate lines of code without use of a new line character, then I can always introduce a semicolon, as I've done there, and now this loop still works. So I think writing a loop like this is prettier and easier to read than writing a loop like this, but this still works. You can add arbitrary spacing and mix up new line characters and semicolons if you want. Okay, so with that, here's the syntax for a for loop in Julia. We have the for keyword now, we have the end keyword, we have this in keyword that allows us to take whatever our local variable in the for loop is over all the values stored inside our loop iterable. And then again, we're just going to have some sort of loop body here. So here's an example of a for loop. We're now using a for loop to count from 1 to 10. One new thing that I'm doing here is I'm using a range. So a range in Julia, we can specify with a colon. So here I have the beginning of my range, the number 1, the end of my range, the number 10, a colon to separate them, and by default I'm stepping through that range with integer steps of the integer 1. If I wanted to take different steps through this range, I could do that, in which case the syntax changes just a little, and now I have 1 colon 2 colon 10. So 2 is my step size, and again 10 is my end, 1 is my beginning. Now I have 2 pairs of colons to separate on either side of the step size to separate it from the beginning and the ends of the range. And here we see that I'm counting from now 1 to 9, printing out only the odd numbers. And as before, we could iterate over an array in a for loop and greet all the entries of that array. One thing I haven't shown yet is array slicing. So let's say that I only wanted to greet the first 2 members of this list. I could say my friends, and then now I can put a range inside my friends. So I could say 1 to 2. Now I'm only greeting Ted and Robin. Similarly, let's say that I only wanted to go from Barney on. I could say 3 colon end, and now I'm going to take the third element of the array towards until I hit the end of the array. So 3 to end gives us greetings for Barney, Lily, and Marshall. Now the last few examples with for loops in this notebook before we move to the next notebook will involve creating addition tables. So when I say addition table, actually I'll just run this so you see what I mean right away. So we're creating an addition table where the addition table is just a matrix where every entry of the matrix is equal to the sum of the row and the column indices. So you can kind of imagine that in this column we've added the index 1 from the current column to the index of each of the rows, and similar going across the array. The way that we created this addition table was that we started by creating an not empty, but a matrix of zeros that we called A. And we created this matrix of zeros using the fill command, where the fill command's first input argument says what we want to create, what we want to fill the array with. So if I had said, fill of 5, I'm then getting an array of 5s. And then this second input argument is specifying what I want the dimensions of that array to be. So we started by creating a 5 by 5 array. Here I'm creating a 5 by 7 array. If we want to bring this back to an array of zeros, I could just say fill 0 and then 5 5. So yes, the point is we started with this array of zeros, and then we used this nested for loop to populate all the entries of that array. Now the nested for loop in this first example is, we basically just use the same syntax for a for loop that we saw above, and then we put another for loop inside it. What we could have done instead is we could have used some syntactic sugar inside Julia so that we only needed to use one for keyword and one end keyword, even though we're actually iterating over a two-dimensional object. So instead of using the nested for loop that we did here, what we've done is we've taken the important stuff basically from this inner for loop, the j in 1 to n, and we've thrown that after the I in 1 to m statement, separating the two statements by a comma. And so now we've again ended up with an addition table, but we have changed the way that we've written this. This can be really nice when you have loops that are very deep. So for example, I could add arbitrary dimensions to this. Oh, it doesn't like that because I already initialized B. So I'm just going to create a new matrix called C here, which might mess me up later. But yeah, I'll do fill. So I'm creating a matrix of zeros, and now I'm going to create a matrix that is m by n by 10, and then subsequently populate it. So the idea here is that sorry, I got quiet for a second. I was sort of talking to myself in my head. Yeah, so the point here is that you can do this sort of syntactic sugar way of nesting loops for arbitrary depth of your loop, which might end up being easier or cleaner if you don't need to worry about your indentation scheme all the way down. All right, so the third way that we might create an addition table, or basically use nested loops to populate an array, is with an array comprehension. Now I haven't shown an array comprehension at all yet, so before you look at that and try to figure out what's going on, let's just do a 1D array comprehension. So in an array comprehension, what we're doing is that instead of creating an array by, for example, populating it manually with entries, there are multiple ways to avoid needing to populate an array manually like this, but basically instead of manually entering entries, I can put code inside square brackets, and then that code is going to get evaluated to generate the array that I actually want on the fly. And so what would that look like? What I would do is I would start with square brackets. I would start like I'm writing a for loop. I would say for example, x in the range 1 to 5. And now I don't need an end keyword. I do need a loop body. The loop body is going to tell me what I'm actually going to do for each of these entries. So let's say that I just want to create an array that stores the elements 1, 2, 3, 4, and 5. I could say x for x in 1 to 5. And now I'm creating the array that has those desired elements. I also could do fancier things inside the loop body that exists to the left of that for keyword. So I could say x cubed, for example, for x in 1 to 5, and now I'm cubing each of those numbers. As with the case of you're adding these arbitrary depth to the syntactic sugar that we saw above for these nested loops, we could create higher dimensional arrays this way. So I could say y in 1 to 5 now, for example. And now I've just created a two-dimensional array using an array comprehension. The array comprehensions that we were doing above to get addition tables looks like this, where now we're saying our loop body is I plus j, and that comes to the left of the for keyword. Note that the highlighted portion here inside our square brackets is really just the statement that we had. Oh, that I deleted? Yes, the statement that I deleted. So previously we saw that we had code that looked like this. So we can just ignore that for a second, the line with C. But yes, so if you were to take this first line from our syntactic sugar version of creating this addition table, you could copy it and then you could paste it right here into this other highlighted line inside of our array comprehension. And what we've done that's interesting here is that we've created an array for the first time without actually, or rather we've created the addition table that we wanted for the first time without pre-allocating an array of zeros. So we didn't use the fill command in the case of working with this matrix called C. Okay, so that's it for notebook 4. We've got 2 notebooks left in our whirlwind tour of Julia's syntax. Those include notebooks 5 on conditionals and then notebook 6 on functions. And after that, then we'll start talking about package ecosystem plotting and then some more advanced language features and that sort of thing. Okay. So conditional syntax in Julia. We have the if keyword, the else if keyword, the else keyword, and then again the end keyword to denote the end of our conditional statement. After if and else if, we have conditions that need to be evaluated, and then else just provides a default behavior. So no keyword or no condition to evaluate there. Now my first example of using all of these different keywords to create a conditional statement in Julia is my implementation of the FizzBuzz test. If you haven't heard of FizzBuzz, you can Google it. It's an oft talked about entry-level programming interview question, where the challenge is that you're given some number, so say the number we're given is 42, or the number n, and you want a program that will look at that number n, and then it's going to print fizz if that number n is divisible by 3, it's going to print buzz if the number is divisible by 5, and you want it to print fizzbuzz if it's divisible by both 3 and 5. So to show you that this works, if I evaluate this piece of code, given that 42 is divisible by 3, we're correctly printing fizz here. Beyond the conditional syntax, some other things that are useful to know when you're looking at this code. The ampersand sign in Julia means and. So when I add the ampersand here, I'm evaluating to see if n is divisible by both 3 and 5. The way that I'm checking for divisibility in this case is that I'm looking at the remainder when I divide n by 3, and then I'm checking for equality with a double equal sign to see if that remainder is equal to 0. Alternatively, I could, for example, delete this bit and use the function called isEqual, and then I can say, I can again ask for the remainder when I divide n by 5 with the modulo operator and say, is that equal to 0? And I should get, yep, the same output when I do things this way. So 2 new things here are the ampersand for and the double equal sign for equality. A related trick in Julia is to write out a conditional statement using ternary operators. I hadn't seen these as a Python user, so I like them. I think they're exciting. Maybe the novelty will wear off one day, but it hasn't yet. So, a ternary operator. A ternary operator is just a conditional statement with different syntax, and this is an example of a ternary operator. So if, or use of a ternary operator rather, if we have a conditional statement like this, where we have if A, so A is some condition and we're evaluating, then B, so B is the thing we do if A is true, C is the thing we do if A is false. We could translate this conditional statement into a conditional statement just like this, where again, A is the thing that we are asking, is it true or false? You can remember that with our question mark. And then B is the thing we do if A is true. And then we have a colon to separate B then from C, where C is the thing we do if A is false. That was a lot of words at once, so I will show you what I mean. Let's say we have x equals 3, y equals 4. Then we have some conditional statement where we're just returning the larger of the 2 numbers by checking, is x greater than y? Return x if it's bigger, return y if it's bigger. I can then rewrite this conditional statement using a ternary operator here, where again we're just saying, is x greater than y? Question mark. I wonder. If it is, return x. If it's not, return y. And we'll print 4 again. Sorry, things scrolled a little weirdly there. But yes, when we run this, we return 4, just as in the case of using more traditional conditional syntax. And then one related thing that I like to talk about when we're discussing conditional evaluation is short-circuiting in Julia. And so in Julia, we can short-circuit, well, okay, before I get to how to short-circuit, what is short-circuiting and like what Why do we need to think about that? All right, so when we say A ampersand B in Julia, or A and B, the default behavior here when we say and in this way is that Julia is going to eagerly evaluate this statement. What that means is that Julia is going to run ahead and look at B and see if B is true or false, even if Julia has already seen that A is false. So once A is determined to be false, A and B is going to be false. So this rushing ahead isn't always, useful or efficient for us. In which case, we might want Julia to, stop spending time doing evaluation of this statement as soon as it's encountered enough information to know that it's going to be false. So if Julia sees A, maybe we want Julia to just stop working rather than continuing to look at B. If we want Julia to stop working after it sees its first indication that it has enough information, then we can short circuit this evaluation. And we short circuit that evaluation simply by using a double ampersand rather than a single ampersand. And I will show you the difference. So for example, let's say x is greater than y, ampersand ampersand print ln x. If we run this, maybe for contrast, I'm going to add another cell here with this plus sign, and I will do the same thing. Select, copy, and paste. Remove an ampersand. Run. Oh. I broke something. Just a moment. There we go. Okay. All right, so I'm kind of cheating. Yeah, I'm cheating a little because when I evaluate conditions like this, I want the conditions to return, true or false. The print ln statement is not returning true or false. So if I'm doing eager evaluation like this with a single ampersand, I get this angry message from Julia because the second argument is returning a void. It's not returning a Boolean value or something that can be evaluated as true or false. So to kind of make this work, what I need to do is add a Boolean value to this second statement after the ampersand. And then it's doing what I want it to do. What I'm trying to show here is that x is not larger than y. When I look at this statement, x is larger than y, and then I have like a print statement in this second condition, even though I've already gotten to the point where I see that this statement, this entire statement here, is going to return a false because the first statement is false, I'm still actually going on to evaluate this second condition. And you can see that because the number 3 gets printed. If instead you add a second ampersand here and you short circuit the evaluation, as we've done here, Julia returns false as soon as it sees a false. It doesn't need to carry on and print x. However, in this case, y is the larger number, so even though we're short circuiting here, we are evaluating this second input and printing the number 4. So this is interesting because this means that we can effectively use short circuit evaluation to do conditional evaluations. I could have, instead of doing this, I could have written something like, if x is less than y, and then I could have had a print ln statement in here. Yeah, so I'm getting the same behavior when I use an explicit conditional here and when I use short circuit evaluation here. So that can be a fun trick and a thing to be aware of. So these examples of short circuiting all use the ampersand or the double ampersand to show eager versus short circuiting behavior. If you wanted to say or instead of and, in Julia we say or with vertical lines. So here we're doing eager evaluation of an or with a single vertical line. So see that even though we've already seen a true, which in this case is all the information we need for an or statement, we're still printing high by moving on to the second statement evaluation. But if we short circuit this OR evaluation by using double vertical lines, we see true and we return, and we never get to the point where we actually print high here. Okay, so one more notebook in our whirlwind tour syntax, and that is notebook 6 on functions. So in notebook 6 on functions, we're going to see first how to declare a function, And then we're going to talk about duck typing in Julia, mutating versus non-mutating functions. I'll explain what I mean by that. And then higher order functions, in particular the broadcast function in Julia. So first off, how do we declare a function in Julia? There are a few different ways to do this, and the first way is to use the function and the end keywords. So the function keyword, after that, we'll add the name of the function that we want to declare, and inside parentheses after the name of that function, we'll put the input arguments that we want to pass to that function. Then we'll put the function body in between the lines that contain those function and keywords. So here I'm declaring this function called say hi that takes an input and then greets that input. In the next function declaration here, we're creating this function called f that's going to take an input and return the square of that input. And then we can call either of those functions by saying the name of the function that we want and then putting inside parentheses the relevant input argument. So here we're passing the input argument that's going to be interpreted inside the function as name, and then we're greeting name here, and then here we're squaring the number 42. Now we also could have declared either of these functions, f and say hi, without using the function or the end keywords. And the syntax that we have for doing that is to simply write the function name, again followed by parentheses that enclose the input arguments to that function. And then we just put the function body to the right of an equal sign that follows that function name and input arguments. So now we're going to have a function called say hi 2, and similarly a function called f2 that again is just going to square input arguments. The way that we would call either of these functions is exactly the same. And so here we're calling say hi 2 on r2d2 and calling f2 on 42. All right. And the third and final way that we might declare a function is to declare a function as an anonymous function. So if you're not familiar with anonymous functions, they seem a little weird at first. When I say anonymous function, what I mean is that I can declare a function that has literally no name, such that I can thereafter not access this function because I have no way to explicitly call it. I would declare an anonymous function like this by putting my input arguments to the left of an arrow, where that arrow is just a dash followed by a right pointing arrowhead, and then I have my function body to the right of that arrow. Now this is a little weird at first because if you're seeing anonymous functions for the first time, you're probably asking yourself, like, why would I ever want a function that doesn't have a name that I can't call after I've made it? And we will see the answer to that question at the end of this notebook. But for now, note that you can do that, and that if you like this syntax for some reason, but you do want to be able to call your function after you've made it, you have the option to actually bind a variable name to it. So I could say the variable say hi 3 is equal to the function over here that's highlighted now, and now I'll be able to call that function using the variable say hi 3. Similarly, I'll be able to call this function that takes an input and squares it using the variable f3, and we can see that the syntax for calling either of those functions is the same as it is in the case of the first two ways that we were able to declare functions. So now we know how to declare functions in Julia by a few different methods or ways. The next section is on duck typing in Julia, and the point of this section is just to show you that Julia functions will work on whatever inputs make sense. So I'll walk you through now what I mean by that. What I mean is that when we define the function say hi, we didn't say hi takes strings and then greets those strings. We just said say hi takes a variable and then it greets that variable. And so when we call say hi, it's just going to work whenever, maybe another note that I should make is the way that we wrote say hi above in each of these versions is that say hi is just going to specifically interpolate whatever input argument you give it into the output string. And so that means that when I call say hi, it's going to be built on the existing string interpolation functionality in Julia. And there are a bunch of different things that you could interpolate in a string because someone else has already provided you with that functionality. So that means when I say hi on, a number rather than a string interpolation is defined for a number just as well as it is defined for a string, and that means that say hi is just, from my perspective, it's just going to work magically on, on this input. Similarly, we used the exponentiation operator to square the inputs of the function f. And we saw that that function f works on scalar inputs, so it squared the number 42, for example. But if we now have a matrix called A, and we call f on a matrix, we see that this is going to work. And the reason it works is that the exponentiation operator that's being called under the hood when I call f is defined for matrices, because matrix multiplication is a well-defined operation, and so we're able to square, we're able to multiply matrices in Julia. All right, similarly, the star operator, and thereby the exponentiation operator, is defined for strings in Julia as a way to do string concatenation, as we saw in Notebook 2. And so that means if I call my scoring function f on a string called hi, I get this concatenated string hi hi. On the other hand, there are some inputs for which a given function call might not make sense, and then Julia will tend to fail. So for example, let's say that I had a vector or a 1D array called v. If I call f, my squaring function, on the vector v, I'm getting an error. And the reason I'm getting an error is that vector-vector multiplication is not a mathematically well-defined operation. It's not clear if the square of a vector means the inner product or the outer product of that vector with itself. And so Julia doesn't take a guess at what you're trying to do. Julia just says, this is a dimension mismatch. I don't know what you're trying to make me do. Okay. So now we're on to mutating and non-mutating functions, and this brings us back to the observation that certain function calls that we've seen so far had exclamation points after them. So for example, we had a Fibonacci sequence, and we saw that when we want to remove a value from an array, we use this pop bang command, where pop bang is followed by, rather, the bang in pop bang is an exclamation point. So why do some functions have exclamation points like this, whereas others don't? The reason is that this is a convention in Julia to denote something special about this function. The convention is telling us that any function that has an exclamation point on the end, any function that ends with a bang, is a mutating function. Functions that don't have a bang would be non-mutating. And so a mutating function is a function that takes some inputs and it actually alters the inputs themselves rather than just generating a distinct output that doesn't touch your inputs. And I'll show you what I mean by that. So we'll look at the difference in a mutating and a non-mutating function and their behavior by comparing the behavior of the sort and the sort bang functions. So to do that, we'll start with this vector v. So it's unsorted and we want to sort it. So we'll start by using the sort function. We call the sort function on v, and now we get this output vector that is sorted. So it starts with the number 2, ends with the number 5. So that's great. When we look at the vector v that we started with, after calling sort on v, we're going to see that v is that original v that it was when we first created it. It has an unsorted set of elements, 3, 5, and then 2. But if we had, instead of using sort, if we had used sort bang and called sort bang on v, we're again going to get this sorted output vector that has the elements 2, 3, and 5. But now, after calling sort bang, if we look at v, v is also that sorted output vector that has 2, then 3, then 5. And so the idea is that, both sort and sort bang are giving us this sorted output answer that we want. But sort bang, being a mutating function, which we know because of the exclamation point, is also updating our input arguments. It's also updating v. Okay, now we're on to higher order functions. If you're not familiar with the concept of a higher order function, they're not scary. Higher order functions are just functions that can also take other functions as input. And therefore, really a classic or common example of a higher order function in Julia is this function called map. What map does is it takes another function, so for example the function f, as an input argument, and then it is going to apply that function to the collection that you pass as the second input to map. So why do we need map? Why can't we just apply the function to the collection? The idea is that when the function map applies the function f to the collection that it's being given, it's applying that function f in an element-wise fashion. So instead of applying f to the vector that contains the elements 1, 2, and 3, it's going to apply the function f to the elements 1, 2, and 3 themselves. And then it's going to return this output array that has that has elements that refer to those answers, those applications of f to the elements of the input vector. So for example, if I call map on f, and then again this vector 1, 2, 3, we're getting this output vector that has the numbers 1, 4, and 9, so the squares of 1, 2, and 3. Higher order functions are a place where we can make use of anonymous functions that really have no way to be accessed after we've declared them. Because as we saw above, the first input to map is going to be the function f, and that means, or rather, it's going to be a function. For example, we pass it the function f. Alternatively, we could just declare a new function to pass as an input to map inside the call to map itself. So here we're saying map, the first input to map is an anonymous function, which just takes an input and cubes it. And now, when we run this line, we're getting this output array that has the cubes of the elements 1, 2, and 3. So broadcasting is sort of a big deal in Julia. It comes up, it can come up pretty frequently depending on what you're doing. And so I just wanted to show you what broadcasting is. For the purpose of this tutorial, we can treat broadcasting like it's map. The broadcast function is a sort of a generalization of the function map, so that means that broadcast can do everything that map can do and more. But for our purposes, we'll treat them like they're clones. So we'll say, okay, broadcast, if we were to call it on f and then this vector, we're again just going to get element-wise squaring of the vector 1, 2, and 3. But what's special then about broadcast, distinct from map, is that the broadcast function can be called without actually saying broadcast. Instead of using the word broadcast as our incantation, we can just add a dot after whatever function we want to apply element-wise to a given collection. So if I call f dot and then throw the relevant vector inside my parentheses here, I'm actually applying f, element-wise to those entries. To drive that point home, let's look at another instance of using this dot after a function call. So here I'm creating this matrix called A. It has the elements 1 to 9 from the top left to the lower right-hand corner. And if we call the function f on A, we're going to square the matrix A. So we're going to get the product of the matrix A with itself. On the other hand, if we call f dot A, we're now going to square every entry of that matrix A. So that's what we're doing when we're broadcasting with this dot syntax. And one of the things that's cool about this dot syntax is that it gives us a way to write more complicated mathematical expressions with notation that looks more similar to the notation that we might use on paper when we're describing our math than if we were to explicitly use a call to broadcast. So it's a little bit easier, I think, to look at an expression like this and have a sense right away of what's going on versus a call like this, where you have an anonymous function and an explicit call to broadcast. Another thing to note about broadcast, if this is helpful or meaningful to you, is that broadcast generates fused operations. So you're not doing temporary allocations of the intermediary results as you apply many operations at once to a given object. All right, so that's it for our whirlwind tour of syntax. I'm going to try to get us through a few more notebooks before we hit 12, and hopefully we can, if I can have this room a bit past 12, then I'll keep going for those of you that are able to stick around. But first, what we'll show are the notebook 7 on packages and then notebook 8 on plotting. And I'll definitely make sure that before 12, I'm going to get to notebook 9 too, which is Julia is fast. So we'll definitely get through all of our benchmarking stuff. And then I might just be a little pressed to squeeze in some of the multiple dispatch and linear algebra stuff at the end. So first off, packages. We said at the beginning of the tutorial that the package ecosystem in Julia is growing and has over 1,900 registered packages. If you want to check out what packages exist and what functionality is already existing and out there for you, you can check out the available packages at either of the links that are provided here. So you can go to pkg.julialang.org or you can go to juliaobserver.com. The purpose of this notebook is really to show you how to use a package. And I'm going to be creating a tutorial within the next couple weeks to show you how to use the package manager, so how to install and load a package in Julia 1.0. The syntax for doing this is a little bit different in Julia 0.6. So I'll show you quickly how to do this in 0.6 so that you understand what syntax I'm using as you look at the code that I have in the upcoming notebooks, but note that these things will be changing and that I'll put out just a short video of a few minutes to show how to do this in 1.0 soon. And so first off, in Julia 0.6, if you want to install a package that you've never used before, so say that you just installed Julia, you want to plot things for the first time, you want to install the plots package, for example, you would use this pkg.add command. And in this example, what I'm doing is I have the code written down to install the example package. The example package, I'll show you what the example package does in a second, but note that on JuliaBox, you don't actually have to run this code. You don't actually have to do any installations because all the packages that we're using on JuliaBox today have been pre-installed for you. But if you're on a local installation and on 0.6, you would install with syntax like this. Once you've done that, once you've installed a package, you never have to install it again for that Julia binary, but you do always have to load that package with the using command. So here I'm using the example package, and that means now that I've used the example package, I've brought all of the code associated with the example package into my current scope. And that means that if I were to go to this file, I would see the source code and I would know exactly what functionality I have access to, which happens to be this function called hello that's going to take some input string and then interpolate that input string into a greeting. So I can call this hello function now because I've used example, and I can use the hello function to, for example, print out some Adele lyrics. Another package I like to demo is this colors package. So we don't have to install the colors package as is done in the note, or the comment is the word that I wanted here. But we do have to load the colors package. So we can say using colors. That gives us access to this function called distinguishable colors, which gives us a color palette, in this case of 100 distinct colors. Now that I have this palette, I wanted to show you an example of using the rand function to do something other than generate a random array of numbers between 0 and 1. So what's happening here is that I'm still using my input arguments to denote the size of the arrays, where those input arguments are integers, but Julia understands that if my first input argument to rand is some sort of collection or iterator, that Julia should use that collection or iterator to draw the random values that we want. So here I'm saying randomly select colors from the palette and generate a 3x3 array, and every time I run this I'm going to get a different checkered matrix. And also, just as a note on the rand command, if you wanted then, for example, to generate an array with integers, you could do something like this, where now I'm specifying the range from 1 to 10 and getting another type of random matrix. So that's how we work with packages in Julia 0.6. Yes, 0.6.2. And now we are going to use in this next, oops, not that one, just kidding, this one. We're going to notebook 8 on plotting, and we're going to use the plots package now in this notebook. So I'm going to start by just saying cell, and I will run all, and then, okay, so in this notebook we're going to use the plots package, as I just said. There are other ways to plot in Julia. For example, you could just directly use the pyplot plotting ecosystem. But what's nice about the plots package is that it brings together a bunch of different ways to plot and gives you one common set of syntax to use so that you can write code to generate a plot, and then you can choose after you've written that code specifically which backend or which set of tools you want to use to actually do the work of generating that plot. As opposed to, for example, starting with pyplot, writing code using pyplot's language or syntax to generate a plot, realizing that you actually want a plot that looks a little different than what pyplot produces, and then switching to plotly.js or GR, in which case you would need to normally change your syntax, like rewrite the code that generates that plot. With the plots package, you don't need to do that. You don't need to update your code when you change backends or when you change which plotting package you're using under the hood. So I'll demo that. I started here by just loading the plots package. Then I added some data that we're going to use for the purpose of plotting. In particular, this is some, I'm sure, very accurate data that I drew from the internet, which for a few years between 1860 and 2000 has global temperatures in degrees Celsius and pirate populations in quantified as the number of pirates in the corresponding years. And so just by looking at these arrays, you can see that I typed in the data from left to right for years going forward in time from 1860 to 2000. So global temperatures have been going up from 1860 to 2000 from left to right, and pirate populations, surprisingly, have been dropping since the 1860s. So to get plotting, you would start by picking your plotting backend, and you can, for example, use the GR backend just by calling GR and then parentheses. You would have to go to the plots documentation to see what backends are available for you. In this tutorial, we'll be using the GR and the Plotly.js backends. And so here we start by loading GR, and then we can plot using the plot and the scatter bang commands. So in this call to plot, I'm saying that I want to plot the global temperatures against the number of pirates, and then I'm adding a label for this plot called line. Then I'm using the mutating version of scatter to plot the same thing with a different label that's now called points. One thing to note here is that, I said that this is the mutating version of scatter. Typically when you call plot or when you call scatter without the bangs, what you're doing is you're just generating a new plot. Every time you say plot numpirates global temperatures, you get a new figure. If you don't want a new figure, because say you want to update an existing plot, then you would use the mutating version of either plot or scatter, for example. So when I say scatter bang, I'm saying I want an overlay of a line plot that I would get with plot and a scatter plot that I would get with scatter. And that's what we get here, this overlay between points and lines, appropriately labeled. We can also, use other mutating commands to further annotate or add additional information to this plot that we've already created using, for example, the X label bang, the Y label bang, and the title bang commands. And so here we're using those to update the plot to have a title that says this plot is showing the influence of pirate population on global warming. And then we have pirate populations on the x-axis and global temperatures on the y-axis, where this is a correlation causation joke. I've had some people look at me like I was crazy when I've done this tutorial, so it's worth noting that this is just a joke. We don't really need to modulate our pirate populations to fight global warming. So with that, one of the things that we note when we see this plot is that it looks a little funny, and the reason it looks funny is because it looks like global temperatures have been dropping. And the reason it looks like they've been dropping is because they have been dropping as pirate populations increase. So Julia by default is plotting our pirate populations as going up from left to right, from 0 to over 40,000. But if we wanted to look forward in time, our pirate populations would actually be dropping. So to get this data to actually give us a view forward in time rather than backward in time, we want to flip our data. And I'm doing that with this xflipBang command. So now we can see what's going on from 1860 to 2000 when we look from left to right. So with that, oh no, okay, let's see. Plotly.js is in a bad mood. What we should be able to do, the point of this next exercise on this notebook, is to call a different backend, Plotly.js, and then use all exactly the same code to generate a slightly different plot without changing your code, just changing this one line that calls the backend. Unfortunately, Plotly.js is in a bad mood, so let's see if I try PyPlot. We'll see if PyPlot is in a good mood today. Trying to remember. Okay, so that works, and then will it generate a plot for me? If it doesn't, I'm trying to think if there are other... I'm trying to remember what the other backends supported by plots are. I don't know them off the top of my head. I tend to use the ones that I demo, or I demo the ones that I tend to use. Yes, okay, good. All right, so PyPlot is working. So we changed this PyPlot backend, and now we get a similar looking plot with slightly different fonts and that sort of thing. If we had done Plotly.js, what's fun about demoing Plotly.js is that you're able to drag your cursor over the data and actually see what the values of those data are. But we can't do that today, unfortunately. And so, having done our intro plotting, let's make sure that we get through the Julia is Fast notebook, notebook 9. Okay. And I'm going to run all again, as I did in the last notebook. So I'll go to cell and then run all, since benchmarking can take a little bit longer since you're running each piece of code many, many times. And I'll explain that in a second. Did I do that? It's still loading, so I'm not sure if, yeah, I'm gonna go to cell, run all again. I don't know if that first attempt was successful. Okay, now it's definitely running. All right, and so the purpose of this notebook is to look at different implementations of the same function and then compare how those different implementations perform so that we can see how Julia performs against a couple different languages and tools that you might be familiar with. In particular, the function that we're going to be benchmarking is our implementation of, well, both handwritten and built-in implementations of a sum function. So that sum function is just going to take a vector, it's going to add together all the elements of that vector. In particular, the implementations that we'll be looking at and comparing in our benchmarking will include handwritten versions of the sum function in C, in Python, and in Julia. My highlighting isn't working, but yes, in C, Python, and Julia. We're also going to be looking at a handwritten version of Julia that explicitly uses single instruction, multiple data. And then for built-in versions, we're going to be looking at built-in versions of sum that come along with Python, that come with Julia, and that come with NumPy. And so we'll see how all these different implementations compare. Now, to do that comparison properly, well, before I get to that, first off, to actually time how long these, or how well these functions, these implementations of sum perform, we're going to be using this 10 million element vector that I've called A. And throughout the notebook, we're going to be doing sanity checks. Those sanity checks will include making sure that every time we use a different implementation of sum, it's giving the same result that it gave in other cases, or approximately the same result. Because we want to know that, when we're calling the sum function, it's actually doing what we think we're doing when we're timing how long it takes to do that thing. So these sanity checks. First sanity check is, okay, when I just use the built-in version of Julia's sum, does it work? And the idea is that we have 10 million elements that are each averaging to about 0.5, and when we multiply together 0.5 and 10 million, we get to about 5 million, and so we would expect that the sum of A would be about 5 million, and that's what we're getting. So sum seems to be generating reasonable results. All right, so how are we going to actually benchmark? How are we actually going to time all of these implementations? We could time things just using this @time macro. If you don't know what a macro is, that's totally fine. In Julia, we know something is a macro if it's if it's preceded with an @ symbol like this, and it's just a different type of command. And so when I call @time on sum, in addition to giving me, calling sum of A is giving me this output 5 million, but calling the @time macro on this piece of code is going to give me the amount of time that it took to actually run that code that it was called on. What we're showing here is that while @time is useful in that it can time things for us, it doesn't give us very precise answers. So when I call @time here, I'm getting a very different answer than if I call @time here. That's confusing. We want more precise measurements, and so we're going to make use of this package called benchmark tools that I believe was put together by a gentleman called Jarrett Rebels. Using Jarrett's benchmark tools, which is very handy, we're going to get a better sense of how long each implementation takes to actually run. Every time we run the @benchmark command that this package gives us, it's going to tell us what was the fastest time that we were able to do this operation, what was the slowest time, what was the average time, how many times did I actually run this operation, to give you a sense of what average means and what best or worst case scenario means. So we'll be using benchmark tools for all of our timings. So with that, we'll start by looking at the C implementation of sum. And one of the cool things that we're seeing right here is that we're able to declare a bunch of C code and subsequently compile that code all within a Julia environment. At the end of the day, having written our code in C and then compiled that code in C, we end up with this function called csum that we can call in Julia from within our Julia environment, and it's generating C code under the hood. So then we do some sanity checks with this csum function. In particular, we're going to see that it generates an output of about 5 million, and then we're going to see that that output, more precisely, is pretty close to the output of the sum function that's built into Julia. So these things are doing the same operation. We're checking that the outputs of csum and sum are approximately equal using these curly braces that you can generate with the instructions shown here. Or you can just use explicitly this isApprox command, which is the function getting called under the hood when we use these curly equal signs. So that's just checking to see that two floating point values are equivalent within some tolerance. After we're feeling confident about csum working, we can now time csum. And so we're doing that with this @benchmark command. And what we get from the output of @benchmark includes this best case scenario, or this minimum runtime of about 12.6 milliseconds. So we're going to take that best case scenario, and here we're grabbing the minimum, or the best case scenario, from all the different benchmarking times, getting rid of our units, and then we are going to store that in an output dictionary called D. And the reason for that is that, as we go, we can keep track of, in one place, all of our timings for these different implementations. And then the plot here is just meant to show you the distribution of, how long different calls to csum are taking. So you can see that things are taking, mostly between like 12 and 16 milliseconds, with again around 12 milliseconds being the best case scenario. So then we'll go to Python's built-in sum. To grab built-in functionality from Python, we're going to use this pycall package. And the pycall package is going to give us access to this function called pybuiltin. And then we're specifying which function we want to grab, and then we're giving it a new name in our current scope. Our new name for this Python function is called pysum. And we do some sanity checks to make sure that pysum is working. Once we've done those sanity checks, we can then actually time how long it takes. When we time, when we time the built-in version of pysum, the best case runtime scenario is over 900 milliseconds. So here about 917 milliseconds. So we're taking that best case scenario, we're adding it to this output dictionary and seeing that it's more than, yes, it's much slower than C. Almost 2 orders of magnitude slower than C. Okay, so now we're going to look at NumPy, because if you're working with arrays, most of the time you would probably be working with NumPy. So we can grab NumPy functionality using this conda package. And when we benchmark NumPy's implementation, it's going to take under 7 milliseconds now in a best case scenario to add together these 10 million elements of the vector A. So there are sanity checks. Here's where we add that best case scenario to our output dictionary. And one thing that we'll notice right away is that Python's NumPy version of sum is actually working better than C. And the reason for that is that under the hood, our C code, is nowhere near, it's not optimized. It's just, the sort of brute force approach that we could take to adding together all the elements of this vector A. Whereas Python's NumPy has C code running under the hood that has been optimized. So that's why it's our best case scenario so far. So then we can look at Python's handwritten version of summing in Python, which, again, we're declaring now code in another language in our Julia environment, denoting it as Python code with this py note there. And then we're calling this new function sumpy, which when we benchmark is taking over a second. So now we really are, 2 full orders of magnitude greater than C when we're comparing the handwritten Python to the handwritten C code. So now that we've seen this, we can start looking at different Julia implementations. And we'll start by looking at the built-in version of sum in Julia, which if you use this @which command, you can see where the code is actually written that declares the function sum. And when we benchmark this built-in version of sum in Julia, we see that it's taking us, again, under 7 milliseconds now to to actually run this function on a 10 million element vector. So we'll add that output to our output dictionary. And one of the things to note at this point is that, Julia's built-in and Python's NumPy are really competing neck and neck. So Julia's built-in is competing pretty heavily with, the NumPy implementation, which is running optimized C code under the hood. But the built-in version of Julia, one thing to note here, if you were to actually go to the source code for that function, the built-in version of sum, you would see that that function is actually written in Julia itself. It's not written in some lower level language to get that kind of performance. So now we can talk about Julia's handwritten version. This is looking really similar to the Python code that we wrote above to implement sum. We now have this function called mySum in Julia, which we can benchmark, and it's taking a little over 13 milliseconds. So it's a little bit slower in this case than the handwritten version of sum in C. And we're adding that to our output dictionary. Now, one of the things to note at this point is that, Julia's handwritten is still super fast. It's not quite as fast as the built-in version, but the margin between our handwritten version of sum and the built-in version of sum in Julia is, it's a factor of 2, basically, difference in performance, rather than, well, for example, the performance difference that you would see between Python's NumPy and the built-in version of Python's sum or the handwritten version of Python's sum. So yeah, that margin between what we can do with Julia's built-in and what we can do just writing our own Julia code out of the box is relatively small. So that's already great. And the fact that Julia's handwritten is competing or starting to approach C speeds is already great. But what's even cooler is that we can make this handwritten Julia code even faster if we just do a minor modification. So the minor modification that we need in this case to make this code optimize is to add this @simd command in front of the for keyword in our for loop. And when we do that and benchmark subsequently, we're getting down to 7 milliseconds for how long it takes to do this operation. And so we'll add that best case scenario to our output dictionary. And then here we order all of our results. And so we see that with SIMD in this case, our handwritten implementation of sum in Julia is looking pretty similar to our built-in version and NumPy's version that's built in of sum. Yeah, and so takeaways, Julia's built-in is great, even though it's, I shouldn't say even though, but noting that it's written in Julia itself. Julia's handwritten is really not that far behind Julia's built-in, which is optimized, and then we can add our own level of optimization with a relatively minor tweak that starts to get us, really close to the speed of built-in functionality that's been optimized by somebody who maybe knew more what they were doing than a newer user might, or than I might. So that's it for the Julia's Fast Notebook. And okay, it looks like no one has taken this room from me. So before people start dropping off, in case you have to go, because I did say that this was going to be a 2-hour tutorial and I fell behind. In the last notebook, Notebook 12, at the very end is where we have a feedback survey. So if you were to go to Notebook 12 and scroll to the bottom, and I'm going to start loading my next notebook on multiple dispatch too. Oh, I might have to shortly log back out and log back in. JuliaBox will typically kick you out after about 2 hours. Okay, but at the end of Notebook 12, if I scroll down here, you will see a tiny URL survey link. And actually, I'm getting a little impatient with things loading. I might switch, yeah, I'm going to switch to a local version for the last few notebooks just to not have to wait for my internet connection. And let me make sure, let's see, so if I go to Notebook 12 now, I want to make sure that you are seeing the correct screen since I've been changing things around. Yes, okay. This is loading. I think it's loading. There we go. You can do it. Sorry, I'm jumping around. Okay, now actually, my impatience isn't paying off very well. I'm gonna flip back to Julia Box for a second. Okay. All right, so notebook 12. At the very end is our feedback survey. So if you have a minute to take that, that would be fantastic. Otherwise, I will get started now on notebook 10 for those of you that have time to stick around to talk a little bit about multiple dispatch, and then I'll jump into some linear algebra stuff. So first off, multiple dispatch is the design paradigm of Julia, and it's perfectly normal if you haven't heard of multiple dispatch before. I hadn't heard of it before I came to the Julia community, but it is what allows us to write really fast and generic code in Julia. So it's an important feature. And to start to explain that feature and give you a sense of what multiple dispatch can do for you, I am going to start by talking about some things that we've already seen. So we've already seen that we can declare functions, and we don't need to tell Julia right away what those functions need to take as input arguments. We can just say f squares stuff, and we don't have to say f squares integers or f squares floats. And then Julia just figures out, I can square integers, I can square strings by concatenating them, I can square matrices. But Julia also figures out I can't square vectors because that's not a well-defined operation. So in this case, we were able to totally just declare a function without specifying what input arguments are required. But if we want to, we do have the option to specify the types of input arguments to be taken by a given function. And we can do that by putting an annotation, a type annotation, after the input arguments that we give to a function during the function declaration. So here I'm declaring a function called foo. That function foo is going to print something, and it is going to take two input arguments called x and y. And then I've given these type annotations to both x and y with a colon, and then string to say that I want x to be a string, I want y to be a string. And you'll note that the input that's getting, or sorry, the printout that's happening in the loop body when this function gets called is a printout that says x and y are both strings. So that means that, as you might expect, if I call this function foo that I've declared on two string inputs, hello and hi, for example, I'm going to get this expected printout that says x and y are both strings. And as you also might expect, if I call the function foo now on 3 and 4, it's not going to work because Julia has no idea what this means. There's no definition existing for foo that works on integers. So we can create that definition if we want to. We can declare foo again, where we say foo takes an input x, foo takes an input y, and x and y are both going to be integers. And then I want Julia to print as much when this function gets called on integers. So we declare this version of foo that takes integers. Now we call foo on the inputs 3 and 4, and we get the expected input now, or expected printout, that says x and y are both integers. Now, where things start to get interesting is that if you call foo on hello and hi, we're still getting the printout that says x and y are both strings. And the reason for this is that when we wrote this second definition for foo that takes two integers, we didn't replace the version of foo, the definition for foo, that took two strings. We didn't rewrite it, we didn't replace it. All we did was we added a second definition or a second method to an existing function. And multiple dispatch allows us to do this. Multiple dispatch allows us to have multiple methods associated with one function, or multiple definitions associated with a particular function name. And so in multiple dispatch, or generally in languages that support multiple dispatch, we have this distinction between methods and generic functions. The generic functions are, what we can think of as being tied to sort of the abstract concepts of roughly what we want an operation to do. Like we have sort of an abstract idea of addition in our head, and our concept of addition as a human doesn't have anything to do with, whether we're adding float 64s or float 32s. Like we don't have to think, very hard about what objects we're adding together. We can add 3 and 4, and the way that we add 3 and 4 is similar to the way that we would add, 3.5 and 4.5. However, on a machine, we need specific methods or well-tailored definitions for how do we actually add together two float 32s? How do we actually add together a float and an integer? And so these specific definitions are the methods that are tied to our generic functions like addition or multiplication. And this distinction means that we as users can just work with these sort of abstract concepts. We as users can just say, I want to add stuff or I want to multiply stuff. We don't have to think about these concrete types on a machine, but we get the advantage of using under the hood code that has been well tailored for those specific types that we'll actually end up using at the end of the day. So we're getting the benefits of this additional information provided to the compiler, the information that might say I'm using a function that's tailored for integers, but we don't have to think about the fact that when we add, we're going to really be adding integers, not floats, for example. Okay, so there's this function in Julia called methods, and what methods does is it allows us to see how many different definitions already exist for a given function. So for example, we can call methods on the foo function that we declared earlier, and we can see that there are two different foo definitions sitting around. So we have this version of foo that takes integers, and we have another version of foo that takes strings. Now this starts to get interesting if you call methods on built-in versions in Julia, because there tend to be a lot. So for example, if we call methods on the plus operator and say, how many different ways can we add things together in Julia? We can see that there are 180 different ways that are built in to add things together in Julia. And we also have, besides the methods function, a function that can give us, or a macro that can give us a sense of what's going on, is this @which macro. So when we call this @which macro on a bit of code, it's going to tell us which function definition or which method actually was the one that got used for this particular set of input arguments. So when I call @which on foo 3 and 4, I can see right away that the version of foo that's being dispatched, the version of foo that's getting used in this case, is the version of foo that's written for int64 as an x and int64 as a y, as our input y. And we can also see that it was at input line 7 in this notebook that the particular version of foo here being used is the one that, or that's where it got written or declared. Okay, so next, what happens when we call @which on 3.0 and 3.0 being added together? So we see here that the version of addition that's getting used is the version that is specifically written for float 64s, even though all I had to do was say, I just want to add things together using this plus sign. So that's great. Let's see. All right, I haven't talked about the type hierarchy in Julia, but we did see earlier that we would sometimes create objects that could take anything, or an object of type any as its input elements. That's to say that in Julia we have this, you can think of the type hierarchy as sort of this way of cataloging the different types that exist, and you can think of it as a tree. And so the top of the tree is the any type, and every single type that exists in Julia will be a subtype of any. Between the top of the tree and the very bottom of the tree, we have these other abstract types called number, for example. So number is an abstract type that could account for any floating point number, any complex number, any integer, but not, for example, strings. So if we declare a version of foo here that specifically takes numbers as inputs, what we'll see is that if we call foo now on 3.0 and 4.0, we're getting a printout that's saying x and y are both numbers. Also, we could use the @which command here, and we could say @which of foo on 3.0 and 4.0. And we're going to see that it's this number version of foo that's getting called. But another thing we'll note is that Julia is always going to use the definition that is the appropriate definition that's the most specific for your input types. So for example, if I call @which on foo and 3 and 4, 3 and 4, the integers 3 and 4 are both numbers. So if we didn't have a version specifically written for integers, we could have used the numbers version, but because we do have this specific version that's tailored for integers, that's the one that gets used when I call foo in 3 and 4. And at the end of the day, we can always go back to declaring functions in a way where we didn't have to specify types. If you don't want to worry about that, that's totally fine. And in that case, the generic version of the function you declare will be the one that gets called when there's not a better or a more specific method lying around. So for example, we didn't write a version of foo that takes vectors, and so when I call foo on to input vectors, I'm getting this any type of foo. So that's an overview of some multiple dispatch stuff. If you want to play around with that more, we have more information in Notebook 10.1 for you. But now I'll start to jump into some of the linear algebra stuff. So I'll quit that notebook. We have two notebooks on linear algebra. The first, notebook 11, is just to show you some high-level syntax for working with matrices and vectors. And notebook 12 is where we start to look more at some, I guess, fancier stuff or more fun linear algebra things. So give this another second to load. Sorry for keeping you over. Another thing I'll note while we're waiting is that when we get to linear algebra, this is another place where there are a couple differences between Julia 0.6, which is the version we're on right now, and Julia 1.0, which has just recently been released. One such difference is that all of the linear algebra functionality that just comes, for free, when I say for free, I mean without any additional installation, as part of the base language, has been exported to a package called linear algebra in Julia 1.0. So that's to say that if you want to use linear algebra functionality in Julia 1.0, you'll actually need to install the linear algebra package and then say using linear algebra. For example, if you want to multiply a matrix by a vector. Okay, so notebook 11, we will see first I'm creating a matrix A with the rand command, as I've done before, and then I'm creating a vector x with the fill command, as I've also done before. So in Julia 0.6 and in the linear algebra package in Julia 1.0, you can just multiply together a matrix and a vector using the star operator. So here I'm defining a linear system, b equals a times x. If you want to transpose a matrix or some other array, you can do that using an apostrophe, and this will give you, a apostrophe will give you the conjugate transpose of the matrix A. If you want only the transpose with no conjugation, then you can just use the transpose function. And here, we're working with all real numbers, so the difference between conjugation and lack of conjugation is absent. So if you want transpose multiplication in Julia, say for example you want to multiply together the transposition of the matrix A with the matrix A itself, you could say A prime star A, or you could just say A prime times A, and Julia can figure out from this that the objects A prime and A are distinct, such that A prime A gives you transpose multiplication. If you want to solve a linear system in Julia, you can just use the backslash. And I'll show in a second that this will work for linear systems of various types. So for example, if I say A backslash B, we're going to get the solution x given a linear system ax equals b. And this will work as best it can when we have, for example, an overdetermined system in a tall matrix A, so a matrix that has more rows than columns. In this case, we're just getting the least squares solution when we try to solve for x. We'll also get the least squares solution with the minimum norm in the case where we're working with a rank efficient problem. So here I've defined a rank efficient problem by creating a matrix from two column vectors, or just two vectors rather, as columns in that matrix, where I've used the same vector for each of the columns. So if I try to solve a linear system that has this rank efficient matrix, rank def, again I'm getting the minimum norm least square solution when I use the backslash here. And we're also going to get the minimum norm solution when we try to solve an underdetermined linear system. So here I have a short matrix A to represent an underdetermined linear system where we have more columns than rows, and we get the best solution we can get when we solve this way. Yeah, and the note here is just about, again, using the linear algebra package explicitly in Julia 1.0, and then there are a couple exercises to play around with. So our final notebook for today, for those of you still with me, is notebook 12. And notebook 12, we'll talk a little bit about factorizations and then taking advantage of special matrix structure and then generic linear algebra in Julia. And so here I start just by defining a linear system. For those of you that are less familiar, there are lots of different ways that you could factorize a linear system or factorize a matrix. Factor? Did I just say factor a matrix? Yeah. Get a matrix factorization or factor a matrix. What you are doing when you do an LU factorization, for example, is that you are breaking up the matrix A into the product of a couple or a few other matrices. So in the case of an LU factorization, you're starting with this matrix A, and then you're finding some other way to express that matrix A as the product of the matrices L and U, where L is a lower triangular matrix, U is an upper triangular matrix, and then there's also this matrix P over here that you could bring to the right-hand side if you wanted to, where that's some permutation matrix. Similarly, I think I show below, if you had a QR factorization, you'd be breaking up your matrix A into the product of the matrices Q and R, where Q is some orthonormal matrix and R is upper triangular. So when we actually do a factorization in Julia, we would do that with, for example, the LU fact command in Julia 0.6. When I do a factorization like this, I'm returning a factorization object, which is just a specific type that's been created in Julia to store all the information that you're going to get out of a factorization. So I have my factorization object from this call to LU fact in this object that I've just called ALU. When we look at ALU, the type is this factorization object, which is called base.linalg.lu. And then I can look inside LU to grab the particular matrices that I broke that original matrix A into. So we equated matrix A with the product of the matrices P, L, and U, and I can look inside my factorization object ALU by putting square brackets after the name of the factorization object and then putting the symbols associated with the matrices that I want inside those square brackets. This syntax is changing in Julia 1.0, so if you don't like this syntax, don't worry about it. Just note that when you have this weird colon and then text thing is how we denote a symbol in Julia. So this is the symbol P, this is the symbol L. I'm saying grab for me the lower triangular matrix L from my matrix factorization here, and then this is the resulting lower triangular matrix. To do the same sort of thing in Julia 1.0, I would just say ALU.L rather than ALU square brackets colon L. Another thing to note is that once you've created a factorization object, you can dispatch on the type of that object to, for example, solve your linear system or calculate the determinant of the original matrix. So, we already saw that if you have a matrix A and a vector of B, you can solve the linear system associated with AX equals B by saying A\B. Similarly, if we've already factorized A and gotten some factorization object that we called ALU, we can dispatch on the type of ALU to solve the linear system this way. Similarly, if we call or ask for the determinant of either the original matrix A or the factorization object ALU, we get the same answer. And similar things apply to all other types of factorizations that exist in Julia, like QR factorizations, eigendecompositions, Hessenberg factorizations, and so forth. One sort of fun thing to note here, in this eigendecomposition code, you can grab the eigenvalues and the eigenvectors of a matrix by looking inside the resulting factorization object. And subsequently, if you take the factorization object that you would get out of an eigendecomposition and you ask for the inverse of that factorization object, what's really happening under the hood is that Julia is making use of those eigenvectors and those eigenvalues to calculate the inverse for you. So that's a fun note. And now we're into special matrix structures. So I'm almost at the end. I think in just a few minutes I'll be done. Special matrix structures. So when I say special matrix structure, what I mean is that you often in linear algebra end up working with matrices that have data stored in patterned ways. So for example, you might have a matrix that is symmetric in that, on either side of the diagonal, actually, I'm not sure if you're looking at the mirror image of me. So from my perspective, if I was looking at a matrix in front of me, I would say, on either side of the diagonal, I have the same values in a symmetric matrix. Or you might have a diagonal matrix where, only the entries on the diagonal are non-zero, everything else is a zero. And you can imagine that if your compiler or if your language, your system generally knows about the structure of that matrix, it can capitalize on that additional information. So for example, if you're working with a huge matrix that is mostly filled with zeros and only has non-zero entries on the diagonal, if you don't have to explicitly multiply 0 by another 0 every time you square that matrix with itself, you can save a lot of time. And you can also save a lot of space in memory if you don't need to explicitly store, perhaps millions and millions of zeros. So if you can tell Julia up front, or if Julia can figure out on its own up front that you're working with, for example, a diagonal matrix or a symmetric matrix, it can do lots of clever things that it wouldn't have been able to do otherwise. So I'm going to demo the importance of that in this section. And we're starting then by creating this large matrix, this 1000 by 1000 matrix called A. And then we're using that matrix A to create a symmetric matrix called asim by adding the transpose of A to A itself. And right away, when we ask Julia if asim is a symmetric matrix, Julia says yes. So Julia can look at asim and see, yes, this is a symmetric matrix. That's great. In practice, it's not as helpful as you might think, because in practice, as you work with matrices and vectors, and just generally when you're working with arrays and numbers, you are accumulating floating point error along the way. And so we can simulate what the effect of accumulating floating point error might be here. And what I'm doing is that I'm copying the matrix called asim. I'm creating a new matrix called asim noisy. And then I'm looking inside asim noisy to just one of its entries, and I'm adding a tiny bit of noise. And the bit of noise that I'm adding, I'll print the amount of noise. So I'm adding noise on the order of 10 to the negative 15. So it's a tiny bit of noise, but it's enough that if we now ask Julia, is asim noisy a symmetric matrix, Julia has to say no, because Julia can't tell if that is intentionally or accidentally added noise. So Julia can no longer take advantage of special matrix structure now that we've accumulated this error. But we, as the user, know that it's a symmetric matrix, even though Julia can't tell. So we can use the information that we have, pass it to Julia, and then Julia will be able to use that to do clever things. We can tell Julia explicitly that asim noisy is a symmetric matrix by using this symmetric constructor. Similarly, if we wanted to say, hey Julia, we are working with a diagonal matrix, or we're working with a triangular matrix, we could do that. And we can do that by using these constructors: diagonal, triangular, symmetric, Hermitian, etc. Whatever your use case might be. I should also note, for those of you that might be interested, you can work with sparse matrices in the sense of sparse but not structured. That's a different data type, specifically called a sparse matrix. I'm not showing that here, but that functionality does very much exist in Julia. But yeah, for those of you that aren't working with sparse matrices or don't even know what that is, that's totally fine. Just, for now, note that if we wanted to give information about the structure of a matrix, we can do that. And that's what we're doing here. We're creating this new matrix called asim explicit. And we're saying to the language, this is a symmetric matrix. And now what we're doing is we are going to do the same operation on all three of these matrices and see how long it takes in each case. We are doing, specifically, we're asking for the eigenvalues of the matrix asim that Julia can tell is symmetric. We're asking for the eigenvalues of asim noisy, which Julia can't tell is symmetric because of noise. And then we're asking for the same eigenvalues from asim explicit, which Julia knows is symmetric because we said so. And the point of this is that we're going to see that things are really fast. I don't know why, sorry, the way that things are printing has been odd. So this number refers to the first cell that I executed here. This number refers to the second, and this number refers to the third. And so the point here is that both when Julia knows that it's working with a symmetric matrix, both because we've said so explicitly and Julia could figure it out, it's taking 2.5 seconds roughly to do this calculation, but it's taking an order of magnitude longer in the case where Julia can't capitalize on the extra information. Another example of taking advantage of special matrix structures here, where we're working with a symmetric tridiagonal matrix, so one that has 3 bands that are non-zero in the middle. It's a million by million, and we see that it takes over a second, just a little over a second, to grab the maximum eigenvalue of this large matrix. But what's cool is that if we weren't working with special matrix structures like this, if we instead had to store all of the zeros and work with all of the zeros in this large matrix, we couldn't even do a calculation like this on my laptop. So special matrix structure can be very useful. And the very final thing in this tutorial is the section on generic linear algebra. So the idea is that often when you have a new language showing up and you want to do linear algebra things fast, you take advantage of existing infrastructure out there in the form of the BLAS and LAPACK subroutines that are out there. And so we'll wrap BLAS and LAPACK to get really fast operations for float 32s, float 64s, for example, complex versions of either of those numbers. But Julia now actually offers ways to do more generic linear algebra, so linear algebra where we can't take advantage of those existing libraries. And I'll demo that by showing that we can do linear algebra with, for example, rational numbers. So a rational number in Julia is denoted by a double slash. So here we have the number 1/2 rather than getting 0.5 and actually just doing division. And here I'm creating a matrix called A rational, which is a matrix that stores rational numbers. And the point is just that once we have this matrix that stores rational numbers, given that Julia offers support for generic linear algebra, we can do things like multiply this matrix by other vectors and get outputs that have rational numbers. We could solve the linear system and get outputs that have rational numbers, and we can do factorizations and get outputs that have rational numbers. So that is it. That is the end of the tutorial. Again, there is at the very end of this notebook a feedback survey that you can take if you're willing to provide a little bit of feedback on how this suited your level. And next month we'll have a repeat of this tutorial where I should actually be using 1.0 for the first time. So that will be exciting, and thank you so much for coming today. So good luck with learning Julia. If you need help, again, as a final note, you can go to any of these resources. So with that, I will cut the stream, and thank you again for watching. Bye.